Okay. So I'm going to present some joint work with Evelyn Hubert, Philippe Moustrou, and Cordian Riener. This is based on our secondment that we did in Tromsø at the UIT. And let me start with a very basic observation about Chebyshev polynomials, which lie at the core of both the things that appeared in the title, namely orbit spaces and the chromatic number. And this is actually the same slide I used at the second POEMA workshop. So I'm sure you're all familiar with this definition. So the condition that you see here on the cosine defines us a univariate polynomial TL of degree L. And you get a sequence of such polynomials right here. A way to look at this. Sorry, I hear you very badly.
Nothing has been said.
Nothing has been what?
Said. No question.
Okay, sorry. Yeah, so in this definition, if you do the following substitution, namely replacing the exponential function with an indeterminate x, you can write this condition in the ring of Laurent polynomials, and you get this formula right here. So an observation that you can make here is that this term, x plus x inverse, is an invariant under a group, namely the group of two elements, plus minus 1, which acts on the ring of Laurent polynomials exponentially. So you change the exponent by 1 or minus 1. And the algebraic way to write this is that the ring of all invariant polynomials, so the Laurent polynomials, which are invariant under this group action, is a polynomial algebra in this invariant x plus x inverse. And this is formally the reason why these this formula up here gives us a polynomial. So there is a way to generalize this, and our main result involves this generalization. So let me state this main result first, and then I will go further into detail. This concept of univariate Chebyshev polynomials generalizes to multivariate ones, and the group that I mentioned before generalizes to a so-called Weyl group, which I denote by W. And then you can also obtain a formula, which I will make more specific later on, that tells you that the ring of all Laurent polynomials, which are invariant under this Weyl group, is again a polynomial algebra. And associated to this group and this group action, you have a orbit space. And our main result is that this orbit space is a basic semi-algebraic set. So it's given by, in this case, n polynomial inequalities. And furthermore, we can give the explicit equations for this semi-algebraic set as the locus of positivity of a symmetric polynomial matrix H. So what I'm going to talk about in this talk is, first of all, I will clarify what I mean by Weyl groups and by orbit spaces. And I will show you a definition of generalized Chebyshev polynomials and come to our characterization of this basically a short overview of the proof of our main result. Then I will explain how this is relevant for polynomial optimization, and finally give an explicit example, which is the chromatic number of Rn, which we can compute using this result as a polynomial optimization problem. So something that connects both these Weyl groups and the chromatic number are polytopes, or rather symmetries in polytopes. So here let's look at an example of the 2- and 3-dimensional cases, which are some of them. For instance, here you have the square and the hexagon, in the 3-dimensional the cube, and the so-called rhombic dodecahedron. And basically all you need to know about these polytopes can be reduced to one part of this polytope using symmetries. So for instance, here in this square, you could draw a diagonal line and a horizontal line, and these define reflection hyperplanes. and the whole polytope gets just reduced to this one piece. We call this part that reduce the polytope to an alcove. And a root system now is basically a set of vectors in Rn that defines such hyperplanes, introducing these symmetries for a polytope. So this is a very informal way to define a root system. For a more formal definition, we would point to the book of Bourbaki, chapter 6, on this whole topic. But we don't have to go into much detail here. The point is that from these vectors defining hyperplanes, you can define a lattice, which I call R, and this lattice is always spanned by n points if this polytope lives in dimension n. So we call them ρ1 up to ρn, and this is an integer lattice in Rn. So the group element that is now defined formally here is the element which gives us the reflection on the hyperplane orthogonal to one of those base elements. So I'm sure this is something everybody is familiar with from linear algebra. If you look at this this map right here, if you would forget about this 2, you would simply get the projection on the hyperplane orthogonal to rho j. With the factor 2, you get the reflection instead of the projection. As an example right here, this is the hexagon that we saw before. A base for this is defined by these 2 red vectors. And the automorphisms, which we write as matrices here, are these two, A1 and A2. And these matrices generate a group. In fact, it's a finite group, and the isomorphism type of this group is the symmetric group on 3 elements, S3. And this is one of the most basic examples for these Weyl groups. So a Weyl group is a reflection group generated by these base elements ρ1 up to ρn, and they must come from a root system. So there is a certain crystallographic property, which I'm not going to focus on here, but that's essentially the gist of it. Now we have this lattice R, and so to introduce now to formalize this action of the Weyl group, we look at the dual lattice, which we call lambda. Say it's generated by n other vectors, which I call omega1 up to omega n. And then I identify the group ring of this new lattice with the ring of Laurent polynomials by saying that the monomial associated to omega I is simply the indeterminate xi. And then formally, we have a ring of invariants in the Laurent polynomial ring, which are all Laurent polynomials invariant under this specific action right here. This leads to a generic definition of a invariant element, which is this orbit polynomial theta alpha right there. And one can show, so this is a well-known result from the book of Bourbaki, that the ring of invariant Laurent polynomials is a polynomial algebra generated by the orbit polynomials, which are associated again to these weights which span the dual lattice of our root system. And just in the same manner as we saw on the first slide, you can then define generalized Chebyshev polynomials by demanding that you write the orbit polynomial theta alpha as a polynomial in these generators, theta omega 1 up to theta omega n. And this gives you a unique polynomial T alpha, basically just coming from the theorem you see up there. So we have these Laurent polynomials now. Compared to regular polynomials, we cannot just define Laurent polynomial functions on Rn. We have to define them on the complex torus, which I denote by Tn. And now, how do we make sense of this concept of an orbit space for this exponential action? Well, what you can do is you can define 2 maps. The first map phi basically is just the exponential function in so you You take an element u of Rn, take the scalar product with all of these omega I, and then take the exponential of this scalar product with an I here. And on the other hand, the other function that you define is the basically the evaluation of a point in the torus at the generators of your ring of invariants. And the image of this map is what we call the orbit space. So I will show you a picture on the next slide of why this definition makes sense, why it is called an orbit space. Essentially, it is coming from the fact that you can also now define a function on Rn to Rn, which is called the generalized cosine function. And this is simply the composition of the two functions we defined above. So what this means is that every point in the image of our function theta corresponds to the orbit of one point in Rn under the action of the Weyl group, which is why this is called the orbit space. And here is an example of the B2 case. So in the B2 case, this function z, which is the composition of the functions I defined previously, has this structure right here. So you can see it's actually a cosine. It's a composition of cosines. And what this map does, so to visualize it, here are two pictures. On the left-hand side, we have R2, where this function is defined. We have the square, which is our polytope. Using reflection hyperplanes, we reduce this polytope to this blue triangle you see here. This triangle is also sometimes called the fundamental domain of this Weyl group. The point is that the image of this function is then the domain you see on the right-hand side. And this is then, so since the image of z coincides with the image of this generator function, this is the orbit space of the root system B2, or rather of the Weyl group associated to the root system B2. Here are some further examples of how this domain looks like. So on the top left, you see the A2 root system. This is sometimes referred to as Steiner's cycloid. And this domain is a well-known object in approximation theory. I will also give a reference later for this. And the other three that you can see are the other two-dimensional cases. Here are the three-dimensional ones. So again, we have A3. This is known as Steiner's hypocycloid. And then we also have B3 and C3. So very interesting domains. What you can observe immediately is that you have cusps in the vertices of this domain sometimes. So not every vertex is a cusp, but at least each of these domains has at least one cusp. And now the question, or the question is, how can we characterize these sets? And the surprising answer is that they are in fact semi-algebraic sets. And our characterization for this involves some rather technical observation. I hope it's not going into too much detail here. So what you can see on this slide is basically a connection between these generators of the ring of invariants, theta omega I, which appear right here, and the elementary symmetric polynomials on the left-hand side. And the relation is given in terms of the orbit associated to the first indeterminate of the to the first indeterminate of the ring of Laurent polynomials. So to make this more precise, let's say the orbit is given by n points, y1 up to yn. From this, you obtain a vector of monomials, y of x. And then for each of the four cases, we wrote down here how sigma of I, so the elementary symmetric polynomial of this vector, can be expressed as an invariant in these generators right there. And this leads to this proposition right here. which states that you can find a polynomial which is univariate in T and has coefficients which are multivariate polynomials in X. And if you replace X by the evaluation of theta at X, at small x, then you obtain this polynomial right here with coefficients given by the elementary symmetric polynomials. And now we can use a theorem from algebraic geometry. This is the Sturm-Sylvester theorem, which gives us basically information about the quadratic form of this polynomial in the proposition. So the theorem states that if you define the matrix H as the trace of a matrix C, given in these terms, so 4 times the matrix C to this power minus the matrix C to this power, where the matrix C is exactly the companion matrix of this polynomial f, then this matrix evaluated at a point Z is positive semi-definite if and only if this point is contained in the orbit space of our Weyl group action. Here's an example of how this matrix looks like in the B2 case. So I wrote the matrix here. As you can see, the degree of the polynomials in the matrix is not bounded by n, which is a bit unfortunate. So we have here a polynomial of degree 2, but the last entry is a polynomial of degree 4. If you want to know how this, where this matrix is positive semi-definite, you can look at the determinant and the trace. So here in these 4 pictures, I showed by a red solid line where the determinant vanishes, and by a dotted blue line, I show where the trace vanishes. Both of these domains are not bounded, but if you take the intersection, you obtain precisely the picture that you saw a few slides ago, namely this orbit space right here, or it is a bit better to see on the bottom right. Now, we now know that we have this characterization of this orbit set as a basic semi-algebraic set. Now, the question is, why should you care about this from a point of view of polynomial optimization? So there is a Positivstellensatz, which is due to Krivine and Stengel, which tells us that if the image of if the orbit space of some kind of group action is given by a semi-algebraic set, I denote this by S, and the index H is supposed to indicate that these inequalities defining the semi-algebraic set come from the matrix H from the previous slide. Then this, knowing this, is equivalent to having a non-negativity certificate for invariant polynomials. And this certificate tells you that an invariant polynomial f is positive, in this case on the complex torus, if and only if there exists a sum of squares polynomial s, so that s times f is contained in the pre-ordering, which is defined by the same inequalities defining the semi-algebraic set. I did not add this here, but there is also another equivalence to this statement, which is a theorem by Ries, I believe, if I remember correctly. And this states that you can represent a linear functional from the ring of invariance to R by a measure if this linear functional is positive on the pre-ordering. I did not add this here because we did not investigate this equivalence very much. I believe this is something that is done by Cordian Riener and one of his PhD students. But we checked that this equivalence that you have usually just for regular group actions also holds in this case of exponential group action. Now let me point out some associated literature to this kind of problem.
Hi, Tobias. Can I ask a question?
Yes, please.
So here you use Krivich angle because you don't have any compactness assumption, right?
Yes.
But if you would have, so are there situations where you could have them and then where you could use Putinar certificate, for instance?
Yes. So I'm not sure if so I mean the assumption depends on the representation of the image, right? It's not just if the set is compact. It depends on these polynomial inequalities we get from the matrix. So we did not investigate this, and I'm not sure if you automatically have that the quadratic module is Archimedean. But you can always add this constraint. So the orbit space or the group action is always compact. And in fact, in our case, you can always put it in a ball of radius square root of n. So
because here you can prove non-negativity of f. But if you want to optimize f, then it's a bit more challenging, right? You need to do a bisection on the lower bound of f. Because you multiply f by s, so s is unknown.
Yep.
So if instead of f you have f minus lambda, then you need to multiply s and lambda. So. But with Putinar, you don't have this issue, right?
Yes, I think this is future work.
Okay.
So, thank you very much for this remark.
Okay, thank you.
Yeah, so maybe this is a good point to ask if there are other questions. Great. So
maybe just to comment. So here you have a non-negativity certificate. So you have a denominator for the representation, the S. So Putinar could not be used. Okay, that's not a question. So,
sorry, can I?
Yes,
But it's not done. Not finished.
but you can ask a question.
So here, f is Laurent polynomial. Is it correct? Or
yep.
Okay. And the philosophy is that you want to use classical real algebraic geometry certificates on this Laurent polynomial to ascertain its non-negativity on this complex torus. Is that the goal basically?
Yes.
Okay. Thank you.
So maybe let me elaborate on this a bit. So getting this equivalence is very easy if you write f not as so it is a Laurent polynomial, but you can of course just write it as a polynomial in the generators of this polynomial ring. So this makes the proof basically a one-liner, or this statement, so that this statement carries over.
Okay.
About this other equivalence using about the moment representation, I'm not so sure yet. So we did not investigate this very well. But it would be nice to say something about measures on this ring of invariance. So originally, this problem, so characterizing invariant polynomials or Laurent polynomials, dates back to Hilbert's 17th problem. And someone who worked a lot on this topic is Claudio Procesi. So he published an article in '78 on positive symmetric polynomials. And a few years later appeared joint work with Schwarz. So this is Schwarz without the T, where he gives a characterization of the orbit space if the action is on the polynomial ring. So this result it does not hold for the exponential action on raw polynomials. It's just for the regular group action on the standard polynomial rings, such as the symmetric group, permuting the invariants. And so this is therefore an analogy to their statement. The thing is that what we proved only holds in 4 specific cases. So if your Weyl group is of one of the 4 times A, B, C, or D, there are also 3 more special types which we would like to investigate, maybe with a unifying theory. This is similar to this Procesi-Schwarz theory. Why this domain is also, so why this orbit space is also interesting is because it is the orthogonality domain of these generalized Chebyshev polynomials. So I did not give you the precise theorem for this. It appeared in a paper by Hoffman and Withers, the proof for that. But the point is that these orthogonal Chebyshev polynomials admit very interesting roots. So their zeros have very interesting properties for cubature rules. And Yuan Shu and some of his collaborators published a result in 2010 where they used the roots of the type A Chebyshev polynomials to get a quadrature rule. And in 2011 was a follow-up with one of the special cases that I mentioned. Also in 2012, Hans Muntekas and some co-authors published work on using these the roots of these Chebyshev polynomials in approximation theory. So more precisely, you can do a sampling on this orbit space and obtain nice points for approximation because they have a very nice Lebesgue number. And in 2021, Hubert and Singer published work on sparse interpolation with these generalized Chebyshev polynomials. And so what I want to do now with the remaining time is give you an explicit example of where we use these equations that we obtained for the orbit space in a polynomial optimization problem. And the problem I'm talking about is the chromatic number of Rn for polytope norms. So you might know the chromatic number of a graph. This is simply the question, how many colors do you need so that if you assign colors to the vertices of the graph, connected vertices don't have the same color. So this is a very easy problem for, I mean, to understand, it's a very easy problem for finite graphs. Computation is a different story. But the interesting question here is what happens if your graph is not finite? What if your graph is not countable? And the chromatic number of Rn is defined by this problem right here. Say your vertices are given by Rn, and then you take a polytope norm, you take a norm, and you say that 2 vertices are connected by an edge if and only if the distance is 1. Then what is the minimal number of colors that you need to color this graph? Well, this is called the measurable chromatic number of Rn. From this definition, it is not clear at all that this is even well defined or that it is a finite number. The first time someone formalized this problem was by Hartwiger and Nelson in the 50s, where they asked this question in dimension 2 for the Euclidean norm. So for the norm where the unit circle is just given by the sphere. And in 2014, there was a very interesting paper by Christine Bachok and her collaborators, where they give a spectral bound, which is a spectral lower bound for this number for infinite graphs. So giving some more tools to analyze this chromatic number of Rn. And this is, so in this work, it was shown how this chromatic number problem is closely related to density of packing packing sets. So how dense can you pack the space with spheres, let's say? This would answer the problem posed by Hartwig and Nelson. In 2019, then Bashok and also Philippe Moustrou published a paper where they showed that this chromatic number is indeed finite and well defined if you have a polytope norm. So if you have a polytope norm, which is, so this is why I started this talk with these polytopes. If this is the unit ball of your norm, then this number is at most 2 to the n. And in fact, they conjecture equality. So yeah, so the work of Christine Bashok associates this problem very well to these packing problems. And I don't think I will go further into detail here. The point is now, how can we formulate this problem, and especially the spectral bound that I was talking about, as a polynomial optimization problem? So if we go back to our polytope, and we have now these, so we have this basis, ρ1, ρ2, which defines our hyperplanes. This hyperplane reduces the polytope to some alcove. And these elements which span the dual lattice of our root system are these omega-1, omega-2. They live on the boundary of this polytope, at least up to some scaling factor. And we introduce now this highest root right here, which is the element of the root system, which you can write in terms of the basis so that the coefficients are maximal. And this allowed us to build a connection to this chromatic number problem. So it's what we showed is that the fundamental domain, so this blue alcove that you see here, is an n-simplex, and it is given by so it is bounded by the hyperplanes orthogonal to the basis. So you have scalar product with the basis is non-negative, and then it is bounded by the scalar product with the highest root. This is supposed to be smaller than 1. And you can show that this is the convex hull of 0 and all these weights, omega-1 up to omega-n, divided by some scaling factor, but this factor is not so important. And this, so taking this domain and taking all the orbits of points inside, which I write by Weyl group times this domain, gives you V of R, which is the Voronoi cell of your lattice. So the Voronoi cell is the set of points which are closer to 0 than to any point of the lattice. And this Voronoi cell then is precisely this polytope right here. So the spectral bound that was proven by Bashok for infinite graphs is this one right here. If you have a centrally symmetric measure, mu, which lives on the boundary of your polytope, of your Voronoi cell, and if you have its Fourier transformation mu hat, then the chromatic number has a lower and upper bound. The upper bound is this 2 to the n. And the lower bound is given by 1 minus the supremum divided by the infimum of your Fourier transformation. So a suitable support in relation to these Weyl groups are points in this lattice defined by these omega-1 up to omega-n. And then we can, so yes. So these points are suitable if you assume additionally that your measure is also symmetric with respect to the Weyl group, meaning that every point in the orbit, so points in one orbit have the same weight in the measure itself. So formally, this measure would then be written such as this one right here. So a discrete measure where you sum up over all points alpha which live on the boundary of this piece of the polytope right here. So this is the boundary of our fundamental domain. And then you have some weights C alpha. and then points in the same orbit are supposed to have the same weight. So you just take the sum over all points in the orbit, which is the sum over all group elements, with the Dirac measure delta A times alpha, and dividing by the order of the group is simply a normalizing factor. So now, why is this then a polynomial optimization problem? So the Fourier transformation of your measure is given by this integral right here. So you integrate the exponential function, and if mu is this discrete measure up here, then you obtain a sum of point evaluations in the support, which are these A alpha. And by definition, this is now a polynomial, which is which is basically written in this generalized cosine function, and therefore you can write it as a polynomial in the Chebyshev. So your Fourier transformation is basically just a linear combination of Chebyshev polynomials associated to these weights living on the boundary of your polytope. What else we need for the spectral bound is the supremum of this Fourier transformation, and this supremum is always assumed in 0. So this is then simply the sum of all the coefficients, and you can choose without loss of generality that the sum of these coefficients is 1. Therefore now, a lower bound for this chromatic number has to be given in terms of the infimum of the Fourier transformation. And we write this infimum as the minimum of this linear combination of Chebyshev polynomials on the orbit space of our Weyl group. Yes. So now, if we assume that we have a solution of this optimization problem, computed by some optimization software, let's say, then the question is, how do we get the best possible lower bound? So in other words, what is the best choice of our coefficients? Because this is something we couldn't specify so far. One thing we showed is that you can always choose your coefficients in a way so that you get a sequence of lower bounds. So these mu hat indexed by an integer and then with a star, they are the solutions of your optimization problem, and you can do this basically for every natural number. Basically, what you do is you scale up your polytope. This doesn't change the chromatic number because it's just a zooming effect. It doesn't change how it doesn't basically change the graph that you're coloring. And then with increasing degree, you get a larger lower bound for your chromatic number, leading up to this sequence right here. So what we don't know, what we would like to know is what's the best choice for these coefficients, and then if we have the best choice, what can we say about the sequence right here? I mean, does it converge to the chromatic number? At what rate does it converge? Does it converge in finitely many steps? We don't know, but we have an example where we can give the answer, and it's actually a very easy answer. So this right here is the cube as the polytope, reduced to some simplex right here. On the bottom left, you can see the orbit space, which is this domain right here, which we can describe as a semi-algebraic set. The Weyl group has this isomorphism type, and your weights are basically the vertices, centers of faces, centers of edges, and so on of your cube. And this generalized cosine function is given by this expression right here. What we've shown then is that the chromatic number in this case is already 2 to the n. I shouldn't say that we have shown that because this result was known before, so we have reproven it with this method using polynomial optimization. And the interesting thing is that the lower bound, 2 to the n, which then must be the optimal bound, is assumed at degree 1. So if I go back one slide right here, if you fix all the weights, which give you scalar product 1 right here, up to some scaling, then what you basically obtain is here just a linear combination of indeterminates. So you have C alpha, X alpha, or well, I should say C1, X1 plus C2, X2, and so on, plus Cn, Xn. And this is then a linear problem on this orbit space right here. And then you can show with a very simple theoretical consideration that this that the minimizer of this optimization problem lies in one of the vertices of this orbit space right here. And therefore, if you then compute everything, you obtain the lower bound 2 to the n. So about the other cases, we are not so sure. Here are some examples of this sequence of lower bounds. For the A2 case and B2 case, it is known that the chromatic number is 4. So what we computed here is, this is, say in the A2 case, this is the degree 1 part, which gives you a lower bound of approximately 3. And then if you go to degree 2, where L is 2, you obtain a lower bound of 3.62. The chromatic number is a natural number, so the bound has to be 4. In the B2 case, similar story. In the A3 case, we went up to degree 3, and we couldn't get the best possible bound, which is 8, and it is known that it is 8. Similar in the B3 case, so we checked some low degrees, and best we ended up so far with a 6.44, which is not 8, and it's also not 7 point something. So we would have to go a bit higher in the degree to show that the chromatic number of B3 is also 8. D4, on the other hand, is a very interesting one, because in the D4 case, it is not known what the chromatic number is in general. The result by Bashok tells us that it's something like, so it's related to 2 to the n minus 1 plus something linear in n. And what you get from this bound in the D4 case is 15. And it would be really great if we would find coefficients and a degree where the where our lower bound is 15 point something, or maybe even close to 16, which would prove that the chromatic number of D4 or of Dn can indeed be 2 to the n. And so just to clarify, we didn't get 15 here. We went up in the degree, got 9.35, and everything else is subject to further investigation. Now let me conclude what I have shown you in this talk. So I've given you a polynomial description for this for these orbit spaces. So these orbit spaces came from very very abstract theory on Weyl groups and root systems. The point is, we have now these explicit polynomial inequalities to describe these spaces, and from this we can now move on to investigate further problems in algebraic geometry on positivity certificates. One thing that is also very interesting with this is how many inequalities do you actually need? So what's the minimal number of equations that you get from your matrix? I mean that you need from your matrix, because generically you just get n inequalities, but we have examples where it shows that this is not necessary. So you can have less than n. And this is also something that Cordian Rina is working on currently with one of his PhD students. It will also be good to have a unifying characterization for all these types in the fashion of a Procesi-Schwarz style characterization. And concerning the chromatic number, we are investigating further this convergence of this sequence of lower bounds. It would be nice to say something about the Dn case, because there things are relatively unknown so far. And one very big problem that we have is we don't know how to effectively compute the best coefficients, because it's not anymore a polynomial optimization problem. Then it becomes a bi-level problem, which leads to a infinite SDP, I think, if I remember the literature by Ni correctly. Anyway, so these are some open problems, and I was asked yesterday what you do here at the Côte d'Azur if you don't do math, and I hope this picture answers this question also. So thank you for your attention.
You? You have questions, yes.
So how were you choosing the coefficient C in your experiments?
We basically sampled on the domain where the coefficients live, which is just a simplex, and then ran the optimization problem for every point, basically, which might be a very ineffective method.
Right. And in order to get the bound on the chromatic number, do you need to know the exact value of the polynomial optimization problem, or is a lower bound enough?
No, that's the good thing. The polynomial optimization solver gives you a lower bound, right? And in the spectral bound, where was it? Ah, yes, here. So if you have a lower bound for your infimum, then this is also leading to a lower bound for the chromatic number. So we are satisfied with a lower bound. We don't need the exact value.
Okay, good. Thank you.
Another question?
Hi, Tobias.
Hi, Kobe.
When solving your problems, can you also recover a way of maybe how to color? So in the cases, for example, where you arrive at the optimal chromatic number, can you also reconstruct the way of how to color Rn?
I honestly don't know. I think there is a way described in the article by Christine Bachok and Philippe Moustrou to do that, but I'm not sure. So it has been a time since I thought about this question. So we didn't figure out from our result here that the bound is 2 to the n how the coloring would look like.
And just to get an idea of how such color rings look sometimes, is it that you color the whole polytope, or can it be really strange coloring as well?
I think it's assigning colors to the centers of the polytope. There are some really nice pictures in this paper I mentioned by Philippe and Christine Bachok on this. So I can send it to you if you want. So there are some nice pictures on how it looks like in the 2-dimensional cases for the hexagon and the square.
Thank you, Tobias.
Thank you.
Other questions?
I have one more. So in the D4 case, you are saying that your basically the hierarchy of your lower bound hasn't converged yet.
No.
So in the other case, so basically what I'm trying to ask is whether you can reasonably check the flat extension property in your polynomial optimization to see whether you actually converged or not.
I mean, sure, you can do that. So what you see here is not the Lassé hierarchy.
Right.
It's,
so actually, you are playing with the degree of the Chebyshev polynomials as well, right? So you're increasing the degree of the polynomials. Okay. And then you're solving just the first order Lassé hierarchy. Is that the case? To get the lower bound on the infimum.
So I mean, maybe I should just say what solver we used. For this, I used the Julia package Mosaic tools with the T-source solver developed by Victor. And there I think so you have the option for first order and then for higher order. But yeah.
Right. And basically the limitation for the D4 was the size of the problem in the end, that you couldn't go to a higher degree polynomial?
No, I mean, we I just have to run more problems. I mean, it was getting these bounds so far was not the focus, but future work.
Okay,
So
thank you.
we were not really limited by computation here, mainly because we were thinking a long time about how to get the right coefficients, because before we try a method and then end up with just wasting time. I hope this answers your question.
Yes, thank you.
Questions on online?
Yes. Monique, you wanted to ask? Go ahead.
But you may go ahead, Didier.
Okay, thanks. I was wondering, thanks, Tobias, for the very interesting account of your work. I was wondering this polynomial matrix inequality description you get. So it has matrix form, and it should be exploited at the level of solving the sum of squares problem. So otherwise, you could take just the minors and scalarize everything. So how do you exploit that, or do you expect this can be exploited?
So in these problems right here, we didn't exploit that. So we didn't use the minors. We used the coefficients of the characteristic polynomial because the matrix is symmetric.
Yes.
But
well, that's what I would call the minors. But also, you destroy the matrix. You destroy the matrix structure.
Yes. Yep.
Okay. And
of course, it would be nicer to use it in.
Yeah, because then you increase the degree, and yes, it would be interesting to know whether you can keep the matrix structure since it comes naturally in your setup.
Yep.
Okay, thanks.
So did you have a suggestion on how to do that?
Well, if you want to minimize a polynomial on polynomial matrix inequality, that's what Jan Zeman was talking about yesterday. So there are plenty of ways to do that, exploiting the matrix structure indeed. But I'm not sure your problem really reduces to minimizing polynomial on the PMI set. This must be discussed.
Thank you.
Question by Monique?
Yes, thanks. Thanks for the nice talk, Tobias. I would have a very basic question about the generalized Chebyshev polynomial, because it went fast in the beginning. So I know one very simple generalization, which is you just take the products of the univariate Chebyshev. And does this generalization fit as one of the special cases you consider for one special root lattice?
Yes, this is so the univariate Chebyshev polynomial is the A1 root lattice, so it's associated to this one. And then, of course, you can build any reducible root lattice from this A1 root lattice by a tensor product, and you get this this multivariate Chebyshev polynomial, but it's in its structure basically a univariate one. So you cannot get the same as good results if you take the A1 root lattice n times compared to if you take the AN root lattice. And I think a specific example for this was given when Yuan Shu I mentioned at some point maybe, was investigating these Kubicher rules, where he was first looking at roots of the univariate Chebyshev polynomials. And he saw that when you take the tensor product, you don't get as good results as if you would just take these generalized ones. I hope this answers your question.
Thanks a lot.
Thank you.
Questions? So I have two questions, in fact. So the matrix H of Z that should be semi-definite positive. So it's coming from so it's a quadratic form or associated to some say linear functional. Can you describe this linear functional here?
Yes, it's basically
like the trace, or
it's coming from the multiplication by the indeterminate t in your ring of univariate polynomials, and the multiplication is in the algebra R of t modulo f of z, where z is fixed or x is fixed or whatever. So in R of t modulo f, basically you get the map of multiplication, and the quadratic form is the trace of this multiplication with itself, and then you end up with this matrix H right here. So if you write this multiplication as a polynomial, you get the companion matrix of F, which is why it shows up here. And then this the reason that you have this 4 times some power minus some other power is basically because we work over the complex torus.
okay. So it's like a Hermite.
Exactly, it's
yes, that's a Hermite matrix. Yes.
Yeah.
That's the moment matrix of the measure supported on the roots of this univariate polynomial in T.
Yeah.
Yes. So the sum is equal sum of.
Yes, with uniform weights.
Okay. So yes. So maybe then this is can be reformulated in terms of the roots of this polynomial, saying that it is positive. Semi-definite positive means that T is positive at the root of F.
Yeah, it means that all the roots in T are non-negative numbers.
So it could be reformulated as a eigen problem. Okay, and the other question is, so you have to find this lower bound for the chromatic number.
Mm-hmm.
Find the C alpha. If I understand well. So what did you look at some bi-level optimization where you try to optimize also the C?
Yeah, we checked out briefly the literature by Nie, who published something on bi-level optimization in 2014 or 16. I'm not sure, but so I didn't find a solver for this problem, and it was described as very difficult because you end up not with an SDP in your relaxation, but with an infinite SDP, I think. And a major problem for these bi-level optimization settings is when the domain on which you optimize is not convex, which is not the case here, for example. So we didn't. We would like to have tried solvers for this, and I'm not very familiar with this topic of this bi-level optimization. So if there is a polynomial optimization software that can solve this this problem, then we would be very interested in trying that out.
So what's possible to do is to basically take subgradients or gradients with respect to the C values of the value of the lower level problem and do basically a basic gradient descent on the C values. That's doable. There are formulas for computing these gradients from the solution of the semi-definite programming problem.
Mm-hmm.
I'm not sure whether that's the best invested time at this point, because I guess you are still gridding at a relatively. But what is the dimension of the C considering here?
So where was it? Yes, so it's at least n, and it's so the number is actually the number of polynomials and n variables of degree L.
Okay. So in that case, it could make sense to actually do this gradient descent starting from randomly sampled points. In that case, already exhaustive gridding is not necessarily the best thing to do.
Okay. What was the name of the software?
So I can send you a reference. It's not really a software. It's a way to compute these gradients with respect to the data of the SDP problem. It's currently a package in Julia. I can send you references to that.
Ah, okay, good. Because this is basically what we exploited here in this result, where the optimal choice of coefficients in this case was a vector that was orthogonal on one piece of this of the boundary of this orbit space right here, which is related to the gradient. So maybe this can be generalized.
But so I think in this, yeah, this is interesting. But isn't it possible also to weaken the problem and to yes, have a weaker problem where you introduce these KKT conditions and solve these constraints with a classical solver?
Maybe, I don't know.
I'm assuming you have some regularity of the solution.
Sorry, just a question. I didn't really hear Milan's reply. Are we talking about bi-level problems where on the lower level you have an SDP?
Yes, that's exactly that. You can compute gradients with respect to the data of the SDP and then you gradient or subgradient descent on it.
Yeah, because we have some work on that done with Yusio Utrata and he wrote a number of papers with Li Chunxi about that, where you have a conic programming problem down on the low level, and then you solve it just by bundle adjust or by some non-smooth code. If the dimension of the upper level variable is not too big.
Yeah, we never tried that, but it could be interesting both for this work and for what we've been doing for dynamical systems. Send us the references, that would be great.
Yeah, thank you.
Thank you. So if there are no more questions, we can thank you again. And I think this concludes the workshop. So thank you to every participant online or here. And so we don't know what exactly where will be the next workshop POEMA. So it's planned in December. But hopefully we'll be able to meet there for the next workshop. So before I wish you a good vacation and rest, and hope to see you physically here. Goodbye.